Hi Orgoers, welcome back. Welcome to the Chapter 21 review video. So today we're just going to talk about the molecular structure of benzene, and we're also going to talk about some of the common reactions that we see at the benzylic position. This review video should be pretty short, and yeah, let's just jump right in. Alright, so let's go over here to the molecular structure of benzene. So we've been familiar with benzene for a while now, even back to Orgo 1, but all we knew at that time was that benzene does not react like normal alkenes. So if I were to see like a reaction, and I drew benzene out over here, and we were doing like hydrohalogenation, we did not observe this product. We did not observe halogenation at the alkene position. That did not happen, so don't think that that is true. That did not happen. So we realized, well, our rationale at that time is that benzene is an extremely stable molecule, and it cannot react like a normal alkene would. And now we're going to talk about why it is a very stable molecule, and that has something to do with the notion of aromaticity. So first of all, if I were to just classify the pi bonds and sigma bonds all the way around the ring, it would be pi, sigma, pi, sigma, pi, sigma. Therefore, that is a very conjugated molecule. It's a completely conjugated system all the way around. Now, if I looked at this diagram over here, if I were to classify that carbon, this would be an sp2 hybridized carbon, this would be sp2 all the way around the ring. So since they're all sp2 hybridized carbons, we can say a couple of things. Number one, that the bond angles are 120 degrees all the way out. All the way around. There's 120 degree bond angles all the way around. And then in addition, if it's sp2 hybrids, that means that there must be p orbitals on every single carbon in benzene. All right? And that will make sense in a second. Alternatively, you have seen me write in my keys that I rate benzene like this. And that has something to do with the notion of aromaticity, where electrons are free to be delocalized and move all the way around the ring. All right. So all of this is related. We know that benzene is a conjugated molecule where there are p orbitals on every single carbon all the way around the ring, which means that electrons can be delocalized and travel all the way around. So sometimes we see this kind of shorthand notation where we have a circle to represent that free-flowing movement of electrons. All right. So finally over here, I took up some snippets from your book, and you can see that we do have 120 degree bond angles around those carbons because they are in plane. We know that these are going to be sp2 to sp2 sigma bonds for those sigma bonds around the ring, and then for those pi bonds, we're going to see those are the p orbital overlaps, all right? And then over here, here's like that notion of there's p orbitals on every single carbon all the way around, and over here, since you can see, I guess we haven't really talked about quantum mechanics, but you can see that the pink lobes all kind of phase together and form this kind of huge conglomerate orbital, and then these blue orbitals all kind of conglomerate together to form another, giant group of orbitals, and then electrons can freely delocalize and move all the way around the ring, and that's kind of why this is an extremely stable molecule, and we saw that they did not react the way that we did with all those other alkene reactions. All right, so that's just kind of like the molecular structure and basis of benzene, just some background. And I did want to make two comments. So Dr. Peterson today in class mentioned these two things, that Huckel's rules of aromaticity will not be tested since we already tested you that on that quiz. We're not going to have you count pi electrons, we're not going to do heterocyclic compounds. None of that's going to be tested, so that's good for you guys. In addition, benzene nomenclature will also not be tested since that was also on the quiz. So you guys can, free up some brain space and not worry about those two concepts. All right, so finally, we're already at the ends of chapter 21. So reactions of benzene, and to me, this is pretty much review. I think we've talked about this before, but benzylic halogenation, so adding a halogen to the benzylic position. So what is the benzylic position? Well, the benzylic position is one carbon removed from the benzene. So it would be that carbon over there, and this is the same molecule, so it would be that carbon over there. So recall that bromine and light, or NBS and light, all go through a radical mechanism. So we can kind of assume that we are going to form the benzylic radical. So that's the benzylic radical. And we said that this radical, since at the benzylic position, can resonate with all of those pi bonds within the benzene, benzene ring, and that makes it a very, very stable, radical. So, we're not going to go through this mechanism because that's an Orgo 1 topic, but you can expect that we have a bromine radical, kind of come in at that benzylic position to form this structure, and it is racemic at that position. You can do the same thing with NBS and light, so you are as well going to go through that benzylic radical, and then you're going to have a bromide source coming from that, so you're also going to get the same product. All right, and that is literally it for benzylic halogenation. As long as you have, a carbon that is, one carbon removed from the benzylic position, you can add halogens with either Br2 in light or NBS in light. All right, that's pretty easy. So benzylic oxidation. So this potassium permanganate, so we have this, molecule, this benzene with all these substituents on it, and we have permanganate over here. And what's going to happen is that we can do oxidation at the benzylic position. So, this is a benzylic position, that is a benzylic position, that's a benzylic position. And we can do oxidation to convert, these carbons into carboxylic acid. So the end we don't go through the mechanism in this class, but I will just draw the product and we can rationalize what's going on here. So we get a carboxylic acid here, we get a carboxylic acid here, but we do not get a carboxylic acid here. All right? So the reason why we get carboxylic acids over here and over here is because there is at least one proton that we're able to extract. So remember, oxidation is the loss of electrons. So if we're able to extract, these hydrogens from the benzylic position, we can, effectively oxidize and place carboxylic acids or carbon-oxygen bonds in that position, and that's what oxidation, the definition of oxidation is. So as long as there is at least one hydrogen at the benzylic position, we can do this oxidation, but you can see over here, since we have three methyl groups, or this isopropyl group, there's no hydrogens here. There are no hydrogens that we can abstract, to do that oxidation step. So that's why we have this product. All right? And let's just move on to a really complicated one. So we get these fused benzene ring structures. So let's just look at all the benzylic positions and see if we have hydrogens there. So here's one benzylic position. Oh, and we definitely have hydrogens there. It's a methyl group. Here's a benzylic position over here. This is the isopropyl group. Oh, and we definitely have, hydrogens there. And then, over here, we have another benzylic position, and there are definitely hydrogens there. And then over here, we have a benzylic position, and there are definitely hydrogens there. So, we basically form this structure. So I'm just going to kind of draw these rings. And I'm just going to, do that shorthand notation. And then all you're going to do is just replace those substituents with carboxylic acids. All right, and that is the end of chapter 21. I told you it'd be a short video. So next we're going to talk about the electrophilic aromatic substitution reactions, and we're going to also talk about nucleophilic substitution reactions with benzenes as well. All right, good luck.